Yes, I did know that.
Let me hear it.
Wait, how do you spell
Laser, L-A-S-E-R.
Oh, okay. Light amplification by stimulated emission of radiation.
Bada bing.
There you go. Or stimulation of radiation. That's sexy lasers. Okay, maybe
we go back to 1917.
Okay.
Albert Einstein.
I love how you just ignored me.
Albert Einstein. Little do most people know that he basically introduced the physics concept of a laser.
Whoa, wait a minute. Are you for real?
Yes. And he should have got a Nobel Prize, but he should have gotten like 8 Nobel Prizes.
Exactly.
He got 1, but he should have gotten 8.
He should have, right.
Okay, so one of them was writing down the equation that allows us to even know and understand that a laser can exist.
Wow.
Okay.
Wait a minute. So there were no lasers, and then he mathematically said, yo, check out this laser.
No. He wrote a research paper establishing the principle of the laser. The laser would take another 43 years before it got invented.
Oh,
That's how ahead of the times he was. Okay.
Oh, my God.
Right. So the way it works is you have an atom and it has electrons.
Right.
And the electrons, if you excite the atom, can have an electron bump up to a higher level.
Okay.
Think of it energy. Think of it as like rungs of a ladder,
right,
or floors of an elevator in a building.
Right.
Electrons can hang out.
They can hang out at higher level.
Okay.
So it's like deuces. I'm going out.
There you go.
Right.
So now there it is. Now the electron doesn't stay there. It wants to. The whole system wants to de-excite, and depending on the energy level, depending on the atom, depending on the conditions, the electron can stay there a short amount of time or slightly longer before it de-excites.
Okay.
That's basic electron transitions in atoms.
There you go.
Basic.
It gets excited and then it calms down.
De-excite. It calms down.
Right.
Correct. Okay. And it does that all by itself.
Oh, nice.
Okay, so now watch. If you send light with exactly the amount of energy to allow an electron to go from here to there, it'll get absorbed, the electron will go up.
Okay.
Then when the electron de-excites, it sends back out exactly that same photon.
Like a club that's reached capacity. Two
One
people
go
in, two people
go
out.
Exactly. And would it be the same? Would it look the same? This would have a photon with the same amount of energy coming out. Now, it turns out that the photon that excited this energy level, this is Einstein's brilliance, if you bathe this set of atoms in those photons will not only excite the atom,
Okay.
they will actively de-excite the atom.
Okay.
Just by being in the bath.
Nice.
It's a spooky fact.
That's kind of the reverse of being in the bath with me. I'm just saying.
So that's the spooky fact. That's the stimulated emission.
Right.
So there's the electron. It's going to de-excite itself
right.
on its own time.
On its own time.
Right. But if you put it in a bath of these photons, it'll make it happen faster.
Right. So it goes up and it comes right back down, but that's all contrived by the bath of photons.
It'll make it come back faster.
Right faster.
And by coming down, it emits another photon.
Right. So now.
So this
Oh
builds,
my
that's
God.
what I'm saying.
Yes.
That's what I'm saying.
Oh, this is so cool.
Oh, right.
Right.
Okay. So you create a cavity.
Right.
A very special cavity with 2 reflective sides, okay? So that when the photon of light gets created, it can stay in there
Right.
and go back and forth and get magnified by this phenomenon.
Right.
As long as this medium has these kinds of atoms that'll respond to that photon.
Right. So you're exciting the atoms, but you're amplifying the excitement. Oh, snap! Damn it! That's amazing!
And we just created the whole acronym, light amplification by the stimulated emission of the radiation.
That is amazing. Wait a minute. He figured this out without being able to test it.
He had an understanding of light and atoms and photons, and out came this calculation. It was a calculation.
Wow.
It was a calculation that should happen. And sure
And it
enough,
didn't happen until 43 years later.
We didn't make a box to have that happen until the early 1960s.
Wow.
Right. And so back then, lasers were like expensive and they were rare. And come the late 60s, early 70s, you know who had a lot of lasers?
Goldfinger?
Oh, Goldfinger. I forgot about that. Goldfinger. He had like some big diabolical, evil man laser.
Exactly. Like the best villain line ever.
Wait, is that the one where James Bond is strapped to a table and the laser's coming right up his business?
You expect me to talk? No, Mr. Bond. I expect you to die.
Was that the line?
That's what the line.
Dude,
that's a great line.
You scare me sometimes. You got to get out more, you know?
It's true.
Get through it. I have a, I don't want to quite call it elevated to the level of a parable, but it's a story in my life that I reference all the time. All right, and I'll share it with you. It's short. I'm in high school. I'm a junior in high school. And I'm going to take calculus. Now, if you didn't know, calculus is way more different from algebra than algebra is from arithmetic. Okay? So whatever it took you to get from arithmetic to algebra, what, X? What number is it? Well, it could be any number. How can it be any number? It's in the equation. It's got to be a number. These are the transitions from arithmetic to algebra. The transition from algebra to calculus is more. Okay? So that's why it's generally not taught in high school. It's a college thing, and even then you wouldn't necessarily have it. So I'm handed the calculus book, and I open the page in the front cover, and there are these equations. And they're using squiggly lines I had never seen before. Half the Greek alphabet is in there. I said, I don't know what this is. And I said, I will never learn this. That's what I said. That's what I felt. I said to this, but I need to know this because the universe is speaking this language. I'm screaming at you, sorry. The sound level's okay? Sorry, okay. All right.
You're excited. This is good. This is
you
good.
started this.
Yes.
All right. So I said, all right, one step at a time. So after the first week of class, I took a peek, still nothing. After 3 weeks and a month, I opened up the side of the book and said, hey, I know that equation. I used that the other day. That's good. I like that. And then as the weeks went on, it was as though this fog began to dissipate. It didn't lift, because that implies now you see, and now you don't, and now you do. It just dissipated. It became more and more transparent. And by month 3, month 4, every one of these equations became my friends. Mm-hmm. I said, I want them. In fact, give me more. And that is my measure of what I need to do if I encounter something which in that moment I do not understand. Is that any worse than you coming upon a book of Mandarin and you don't know any Chinese characters? You say, I don't know any of this. Yeah, except 1.5 billion people in the world speak it. So it can't be impossible to learn. Mm-hmm. So you put in the time. And slowly some of the characters, that means a human, or that's a home, or that's a food. And all of a sudden the characters start making sense. It's not really any different from that. Mm-hmm. And too many people think that they got to know something instantly in order to ever be good at it. Rather than want to achieve something, realize there are these hurdles, work at it. And every bit of yourself you invest helps to dissipate that fog. Mm-hmm. And the more badly you want to get there, the more you will work to dissipate that fog. Mm-hmm. And that's what happened to me, and I've invoked that ever since. Yeah,
and then the love with that, too. The more badly you want to get there, and you
the love.
better love it, too.
You got to love it, otherwise what's going to keep you going?
Yeah.
And don't hesitate to ask for help. You know? I've been tutored.
That's you sound like my mother right now. She's over there. Ask for some help. Yeah.
Okay, I've tutored people in my life in physics and in math. I've been tutored. They're not going to end in your lifetime.
In that case, I take it back.
All right, so let me give you some scenarios that are on the docket.
Okay.
As you may know, we are currently expanding.
Yes.
All right.
That's right. Growth, damn it.
And as we expand, the universe gets thinner and thinner, less and less dense.
If you're not growing, you're dying.
Well, consider, how do you make a star? Well, you have a gas cloud and it collapses
right,
to make a new object.
Right.
But if things continue to expand, then there's an interesting sequence of events. First, there are galaxies that have already used up all their gas.
Okay.
They have these elliptical shapes. We call them elliptical galaxies.
Oh.
They don't have any gas, but they have stars that will live 1 trillion years.
Wow.
After 1 trillion years, those stars start dimming out one by one.
That's the actual sound that a star makes when it's
in the vacuum of space.
In the vacuum of space.
They will pluck out one by one. trillions of years from now, because that's their life expectancy.
Okay.
They're burning their fuel very efficiently, very slowly and very efficiently. These are the dim red stars, of which there are many in every galaxy.
Right.
All right. But there's no gas in the elliptical galaxies. There's no fresh generation to be made. All right. In spiral galaxies, such as ours, the Milky Way, we have stars that will also live 1 trillion years. They'll pluck out at around the same time these other stars do, but we have residual gas.
Right.
So we're making stars today.
Yes, stellar nurseries.
Yes.
Yep.
Yes, the JWST.
That's it.
Is all up in that.
Yeah.
So that will only continue until there's no gas left.
Right.
So for a spiral galaxy, it might go another 5 billion years, perhaps.
Oh, okay.
And when we run out of gas, that's the last generation of stars to get made. You're literally out of gas.
Out of gas. Right. That's when the universe makes this sound.
Oh, by the way, in the distant future, as we continue to expand, galaxies will expand beyond the horizon that we have established from our location here. So what is that horizon? That's where they're moving away from you faster than the speed of light. So their light tries to reach you,
but it can't.
It can't. It can't.
Wow.
All the energy gets sucked out of it. And so every galaxy in the night sky will go beyond that horizon. Okay?
Wow.
With or without its stars, it'll go beyond the horizon. So if we look outside of our own galaxy, there'll be nothing there.
Oh.
As far as we know, our entire universe is just the stars, living or dead, in the Milky Way.
In the Milky Way. Oh, that's...
So our entire understanding of cosmology in a post-apocalyptic civilization in that very distant future will have no idea the universe had a beginning at all, because we know about the beginning by looking at other galaxies.
Right.
So a page in the history of the universe will have been removed, and they will not even know it.
Look at that.
But wait, there's more. There's the matter of the black holes.
Okay.
Okay?
Interesting.
All right. So the black holes, the small black holes, actually will evaporate.
Okay.
Okay, using Hawking radiation. Right. So just outside the event horizon, there are these spontaneous particle pairs that are formed out of their gravitational energy field.
Right.
And one particle escapes, the other falls in, and that effectively subtracts mass from the black hole.
Okay.
So we will lose those black holes in 10 to the 30th years, something like that.
Okay.
And around then, our best hypotheses for the survival of the proton.
Okay.
Okay. We think the proton might decay. If the proton decays, that's it. The proton decay, we're thinking also happens at around 10 to the 30th years.
Wow.
Last I checked. It could be an up to maybe 10 to the 32 years.
Right.
But that's around where
but who's counting?
Who's counting? A factor of 10 or 100. Factor of 10 or 100. Who's counting? When we have factors of trillions and gazillions.
Right.
All right. That means the structure of all matter, which is our foundation, is on the nucleus composed of protons.
That's right.
And neutrons. Right. But free neutrons decay.
Right.
But protons are the stablest particle we know. They're gone.
Right.
Okay.
Well, that's it.
But wait, there's the supermassive black holes in the centers of galaxies.
All right.
They take longer to evaporate.
That's true.
They'll still be there.
Right.
They don't just go away just because the universe expanded every other galaxy out of the way and just because all the stars died. How about those? They take 10 to the 100 years to evaporate.
Wow.
You can do the math on this.
No, I can't. This is what we fail to realize.
You know what 10 to the 100 is? What number that is?
10 to the 100?
Yeah.
That's 1,000.
10 to the third power is 1,000.
Yes.
10 to the 100th power, that's a Google.
I did not know that.
So that's a lot of years.
That's beyond a lot.
Okay, that's a lot of years.
Yeah.
All right. So all matter is just scattered evenly into the vacuum of space, whatever's left of matter, and the universe dies. There's no more phenomenon to happen.
Okay.
You don't even have black holes evaporating.
Right. Everything's done.
And the temperatures have been dropping the entire time. Early on, it was very hot.
Right.
It was glowing hot.
Glowing hot.
Right now, it's cooled to 3 degrees absolute zero.
Right.
That's very cold,
Right.
but it got even colder.
Even colder.
Oh, to near absolute zero in the very distant future. Okay? So in that scenario, the universe will not die with a bang, but with a whimper. And not in fire, but in ice.
Oh, that sounds cold and lonely. That is a cold, lonely
That's
ending.
one scenario. Okay? So for a while, people call that the heat death of the universe. But these are thermodynamicists saying that because to them there's no such thing as cold.
Right.
There's only heat or the absence of heat.
That's it. Right.
So the heat.
So now all the heat is gone.
So they call it
heat death.
But that's so misleading.
Exactly.
So I just prefer to call it the big freeze. So let's keep talking about dimensions. Ready? So we have one dimension, which is just a line. The measure of the line is the length. Okay. There's no other measurement you can make of it that has any meaning. Right. It does not have a width. Now you can add another dimension. Let's call that X. We add a Y. And now you have a surface.
A plane.
And that it's two dimensions, X and Y. Okay? So you can make a square out of that, couldn't you?
Yeah.
Two-dimensional beings who live in that surface. To everyone else in that surface, they only have an outer perimeter.
Right.
You can't see inside their bodies.
They're all inside the flat plane.
They're inside the flat
all
plane.
they can see.
All you see is the edge of them.
Right, the edge.
So medical surgery in a two-dimensional universe, they'd have to cut you open, part you, and then reach in and do what they need to, come out, and then stitch you up again. Okay?
Right.
If we live in 3 dimensions, you get to look down on that flat world and see all the inner guts of every living creature in that universe. Because there is no boundary above and below. It's only within the plane itself. You can see the heart beating, you can see the spleen, the liver, the pancreas, the lungs. You can see it all. In fact, if you wanted to be a surgeon for that world, you could go in, cut out the appendix if they needed appendectomy, and never have to cut through their outer boundary. You'd be like magically going into their body.
Dimensional surgery.
Dimensional surgery. They would have no access or even awareness that that was even possible, but you do.
Right.
And you can go in and rectify that. So now, we are in 3 dimensions. We reveal our skin in all directions to the other people.
Right.
So our skin is the boundary between our innards and a medical doctor. If they want to get inside you, they got to cut you open.
Right.
A 4-dimensional creature can just look inside our bodies.
Oh, I feel violated.
I know.
Oh. I hope no one's watching right now. God.
Anyone from the 4th spatial dimension has full access to your entire body's innards.
Oh.
They could pull stuff out, put stuff in, operate, whatever.
We are the game operation to anybody in the 4th dimension.
What I'm saying is, if you had what you beautifully refer to as dimensional surgery, you would be able to operate without ever cutting someone open, provided you come from a higher dimension inward.
Right.
And it is completely analogous to be a 4-dimensional surgeon operating on us without cutting us open, to be we as 3-dimensional surgeons operating on 2-dimensional creatures, because you could just see all their organs just sitting there. Now, we can move forward and back, left and right, up and down. Okay? Those are the 3 spatial dimensions. But the time dimension, you don't have access to the past or the future. We are prisoners of the present, forever transitioning between our inaccessible past and our unknowable future. But let's think this through. How would you imprison a 2-dimensional creature?
Draw a line.
What kind of line?
A square.
A square. Just draw a square. That's its prison cell.
Yeah.
But we say, wait, just step up out of it and then you escape.
Good to go.
I don't know what you're talking about. I'm fully locked in.
Fully locked in.
How do we put us in a cell? We have 6 walls.
Right.
A ceiling, floor, 4 walls around us.
Right.
We think we are completely contained within it. A higher dimensional creature says, just step out and then step back in and you're outside the cell. We said, I don't know what you're talking about.
Right.
Wait a minute. I said a 4-dimensional creature. If we had access to the 4th dimension, which for us is what?
Time.
Time, but wait, we're prisoners of time. So suppose we weren't prisoners of time. Suppose you could move through time the way we move through space. Could you then escape the prison?
Yeah, just move to a time when I'm not in prison.
Exactly. Just say, let me get out of these 6 walls here. You just go back to a time before you got put in a prison, or go to the future where you were let go from the prison.
Right.
Each of those counts as escaping the prison without ever breaking down the wall.
Right.
So time can serve that same role if you had access to the past and to the future.
That's pretty cool, man.
Of course, we go higher to this, 5th dimension, 6th dimensions, this sort of thing. And mathematically, you can calculate what all the properties are. And it's fascinating to watch. Another quick one. You ready?
Go ahead.
Knots in strings only exist in 3 dimensions.
Okay.
In other words, in a 4th dimension, you hand them a knot in the 4th dimension and say, wait, just pull the ends.
Right.
And it unravels itself. That's the same thing as we 3-dimensional people looking at 2-dimensional people, and they have a string that just has this loop in it. One loop.
Right.
And they say, how do I untie this? I can't untie. Say, dude, pick up the 2 ends and stretch. They can't do that.
Right.
They can't do that. So knots are different things in higher dimensions. The way to do it is you have to make a knot out of a 2-dimensional ribbon. And there are ways to do that, I think, and rather than just out of a string. So a lot of interesting things change and are mind-boggling for ascending to a higher dimension.
Sweet.
One last quick thing.
Mm-hmm.
Why does anyone want a flying car?
So you can get up and over traffic.
So you only really think about flying cars in cities where you're like plugged with traffic. And what a flying car gets you is another dimension of travel.
True.
You know, I'm stuck in a 1-lane road because that's bad. All right. But even if you go 2 dimensions and you have multiple lanes, because now you're in a plane, that can get cloggy too.
Right.
So get a 3rd dimension is wide open. But wait a minute. That means we already have flying cars. It's called the subway.
Ooh.
Instead of being in the air, it's underground, bypassing the traffic you're in. It still invoked the 3rd dimension. But also, it means overpasses, where the freeway goes right through and the overpass goes over. That's a flying car right there. You invoked another dimension.
You have a very low bar for what's called a flying car. I'm just saying.